Okay, so we've learned a bit about different types of DNA damage, and now I'm going to talk about how these types of damage are repaired in cells. And we have a tradition in this class where now I ask you some questions and you respond. So the issue is, I've shown you a bunch of damage, but how really bad is it? You know, how much damage does a normal cell get? So this is an example of alkylation, and I guess what I've drawn here is alkylation of adenosine by accidental methionine to give this 3-methyl thing. So how many times do you think this happens per day in a typical human cell? 10 to the 2. 10 to the 2 is 100? 10 to the 4 is 10,000? You're close. Anyone else want to hazard a guess? Too big. Well, you guys think you're all pessimists, I guess. You think it's way worse than it is. Who said 10,000? Okay, you're the closest so far, so it's about 5,000. And for being close. Now, in my experience, the answers start coming a little faster at this point. Okay, so this one is spontaneous depurination, which we talked about. So the loss of this base to leave an A basic site. So how many per cell per day? Oh, okay, that's totally counter to my expectations. You guys all looking it up on your phones? Come on, that's a bad strategy. Shout a number. Oh, 10,000. There you go. See? Class is exhausting. Mr. Golden Sun. Peak hour sunlight. Who said 100,000? Somewhere over here somewhere? 100,000. Thank you for meeting me halfway. Okay, so the point, of course, is that there's a lot of DNA damage events happening per cell per day. There's a huge damage load on cells, and of course, if we bothered to make a high-fidelity copy of our DNA through this complex replication process, you can imagine now we wouldn't just want to sacrifice it at the hands of all these DNA damage events. So DNA repair is an extremely important property within a cell, and it's critical to the maintenance of high-fidelity copies of DNA. So what I'm going to do is I'm going to step through a few different repair systems. As I mentioned, I'm not going to have time to talk about all the different kinds of repair. I deeply regret not being able to talk about double-strand break repair because it's super important and super interesting, but it's also super complicated. So what I'm going to talk about, sort of in order of complexity, are 3 systems, starting with direct repair. And direct repair is possibly the most kind of straightforward of all the repair, because what it involves is simply repairing the damaged base in one step. One step. And what this essentially is just a reversal. So it's kind of a reversal of the damage that initially occurred. So the example that I'm showing you, and let me just preface this by saying that because these are very specific enzyme-catalyzed reactions, these reversals, the range of damage that they can act on is small. So these are enzymes that have specific substrates, and they catalyze a specific reaction. But for example, the repair enzyme that can reverse methylation of O6 of guanine is not going to be able to fix other kinds of lesions. It's not going to be able to fix a deamination of cytosines, for example. And so the spectrum of mutations that you can repair by this kind of mechanism is limited. You also can only repair things that you've seen a lot before. So a novel kind of adduct, say DuPont decides to make some new alkylating agent that leaves some new bulky adduct that a cell's never seen before. It's obviously not going to have an enzyme already in hand to direct the repair. But that being said, for lesions that happen at a high frequency, and as I mentioned, O6-methyl-G is a very common oxidative lesion in DNA. It might make some sense for cells to have dedicated pathways that can simply reverse these changes. So there's the methyl group on O6-methyl-G. So that's what we want to get rid of. Here it is. Here. So basically, the enzyme that does this is called MGMT. And as I mentioned, it's a one-step reaction. And the way this works is that in the active site of MGMT, there's a cysteine residue. And the cysteine residue essentially catalyzes a transfer of the methyl group from the O6-methyl-G to this active site cysteine. And what's kind of weird about this is that the transfer of the alkyl group actually irreversibly inactivates the MGMT. So it's like the sting of the bumblebee. It's only got one go at it. So once this active site cysteine has become modified by methylation, this enzyme actually just has to be degraded. And so one sort of interesting thing that results from this is that the capacity of a cell to repair O6-methyl-G has entirely to do with how much O6-methyl-G the cell can synthesize. So if you were treating, say a hyperproliferative cell with an alkylating agent, and you wanted to kill the hyperproliferating cell, you'd have a better chance if it was a low expressor of MGMT than you would if it was a high expressor of MGMT. Okay, so how's this transfer actually work? It's pretty straightforward. So the mechanism is shown here. So again, this is the active site cysteine. This is the methyl group. And so attack of this carbon by the cysteine results in methylation of the active site residue, and you restore the guanine residue where the O6-methyl-G was present before. What I'm showing at the bottom here is a crystal structure, and the structure is over here, MGMT, and over here, DNA, and not surprisingly, the DNA has one modified base that is O6-methyl-G. Okay, so what happens when